that is also as close as we get to a real world like WWE.
Okay, finally gonna get started. Took me a while to get my little dongle working here. So, thanks for joining me today for your Thanksgiving holiday instead of traveling to be with your families and things like that. Though for you people who are completely local, good for you. But anyway, so today we're going to be talking about this is like the first of these sort of optional topics for the term. This is going to be a lecture on mapping, focusing on mapping using ggplot in particular. There's other ways to do mapping in R, but the ggplot methods are pretty straightforward and are very generalizable. Yeah, so we're going to get into it here. So, what we're going to cover today is using the ggmap package for what I might call mashing up maps with ggplot. That is, being able to plot things normally with ggplot on top of maps that are scraped or grabbed from different websites. So it does things like grab maps from Google Maps, all different types of Google Maps maps, from Stamen maps, from OpenStreetMaps. It just sort of automates the process of grabbing maps, importing the coordinates, handling all the stuff behind the scenes that's normally kind of hard to deal with if you're working with geospatial data. Then we're going to talk about labeling points and using the ggRepel package to nicely put labels over the top of sort of spatial plots. I'm going to talk a little bit about mapping with raw ggplot. That is, instead of using ggmap, how do we just plot maps straight in ggplot based on the idea that longitude and latitude are just x and y coordinates. So you can plot a map in geospatial stuff as you would be plotting any kind of points and lines. And then I just added a section to this lecture on the new package Tidy Census, which is a tidyverse sort of way of grabbing American Community Survey and census data directly from the US Census. So you have to get a census API to do it, but you can just grab data straight for it. It automatically pops it out in tidy data format, ready to shove right into ggplot. So if you do anything with any kind of census data at any level, tract, states, cities, whatever you name it, that basically automates all of the complexities of that process. And then linked to that, I'm going to talk a little bit about the SF package, which is sort of the emerging new standard for geospatial data in R based on the way they store data in GIS platforms.
When did that Tidy Census package come out?
I'm not sure. It's actually not even on CRAN yet. You download it from somebody's GitHub still, unless maybe they may have added it on CRAN. It's really new, and it's really cool. I already messed with it and already integrated into a bunch of the actual work that I'm doing, like my work with Ross and stuff like that. It's amazing. I have a bunch of examples. Okay, first thing I'm going to do is give a quick plug here. So if you're interested in doing mapping and GIS stuff in R in general, especially geospatial statistics, get this book. This is the best book there is out there. It's basically the Bible of spatial analysis in R. So the authors of this, By Van Ledesma and Gomez Rubio, are the authors of the SP package that all the spatial statistics and stuff in R are done in. They're also the authors of the SF package, the new spatial statistics package, and they also wrote the best book on it. So every person I know who does geospatial work in R always recommends this book first, so I'm also going to recommend this book first. If you want to do spatial statistics and serious spatial data analysis, I might recommend CSSS508, which is Statistical Methods for Spatial Data with John Wakefield. It's a pretty challenging course. It wouldn't want to be the first CSSS stats course you want to take. You want to take it after something like MLE and probably also after something like either categorical data, Bayesian stats, or event history modeling. It's a fairly tough class, but it covers a lot of material, and by the end of it, you've gone all the way up to using the absolute cutting-edge spatial statistics methods, which is stuff using the in-law package, and that's what the stuff people on campus are using for the really advanced spatial stuff. It covers everything. Tough class, but worth it. And then lastly, if you want to get into using GIS using established GIS platforms, that being QGIS or ArcGIS, just about every term CSD offers a couple workshops on using GIS. So we're taking, they're free. You just kind of drop in, and they're most of few hours in 2 different days, usually subsequent Mondays or something like that. Anyway, lots of options, and also we have a really good geography department and a really good epidemiology program that has good classes that also cover spatial stats and spatial analysis. A lot of resources. Okay, so first thing we're going to talk about for spatial analysis in R is the ggmap package. So what ggmap is it's a package that goes with ggplot that allows you to plot spatial data directly onto images of maps. That is raster images. We call like something that's rather than being drawn with lines and points, it's drawn with pixels. So like a stable image here. Obtained from Google Maps, OpenStreetMap, and Stamen Maps. And Stamen Maps are ones that are good for sort of minimal options or things that look like civil engineering maps, or they look like they're artistic options too. I'll show some examples of them. What this package, ggmap, will do is it will automate the process of querying some server to get a map using the getMap function. When I say query a server, this means it will query up Google Maps at the location you look for, at the resolution that is sort of like the height you're looking down from, select like street view, satellite view, any of those kinds of things, and we'll grab that image of it, plot it to the correct size for your whatever plots you're going to be doing on top of it, automates the whole thing. It will then plot that raster image as a ggplot object that you can add stuff to, and then it lets you add more ggplot layers, that is things like points, density plots, text annotations on top of it, and it takes care of lining up the XY coordinates of those new geometries you add with the latitude and longitude of whatever geographical thing you've got. It also has some additional functions for interacting with Google Maps, things like getting distances between places, for instance, like distance by bike, distance by car, walking distances, as calculated using the Google Maps API. So it can do a lot of different things that are pretty neat. Might be able to think of reasons to use those too. Okay, so back in week 5, I used some Seattle Police Department incident data. That was sort of incidents that the Seattle Police Department responded to within a single day. So what we're going to do is we're going to map and see where those incidences occurred, or where those incidents occurred in Seattle. What I'm going to do here is I'm going to load up the Tidyverse package and the ggmap. I'm going to read in the data straight from my GitHub, that is where the website is hosted. And then I'm just going to run qmplot. Qmplot is the quick map plot function in ggmap. It sort of takes default geometries and things like that and just spits out a quick point map for whatever you give it. So the only thing I did here is I said qmplot, the data is equal to SPD raw, which was this data I read in here. I just say x is longitude, y is latitude. The color is fire brick, because I wanted red points, because it might be hard to see black-white points. And I made them about half transparent. Then it spits out this. So this is a map, the default type of map given by qmplot. I forget exactly what this is. It's a, you can see that there's major streets shown here. It's centered on what we call the bounding box of our data. So it saw where all the incidents are located according to latitude and longitude, and then it chose a window to sort of grab a Google map to print it so that all of the data would be lying within this box with a little bit of buffer around the edge. So you see I gave it essentially no options here, and it printed a pretty nice point map of all of those incidents. So qmplot is just quick map plot, has great defaults, spits out something that looks pretty good. You can give it additional options if you do like $qmplot in the ggmap package. You'll see that it can take a lot of options, but by default, it puts out kind of nice maps for just sort of scanning and looking at your data. Right? Okay. So you can also do mapping without any data at all. So what I've done here is I've used the qmap function again, but then I've just given it a location. And the location I've given it is basically a Google query. I said, location, Mary Gates Hall, University of Washington, as if you might type in like the Google search bar or something like that. I've said zoom equals 15, and that was something I just sort of tested to get it to focus more or less on the University of Washington. Chose Mary Gates Hall because it's pretty central to campus. I said map type watercolor, which is a type of Stamen map that's artistic. It looks kind of like watercolors. And I specify here source Stamen, because that type of map has to come from Stamen. So I haven't given it any data, but I've just queried a raster map grabbed from Stamen. And this is University of Washington, with sort of roads done as orange, buildings kind of done as a darker blue, open space as a light blue. Printed a nice little watercolor map of the University of Washington, given what is basically just a search query. Right? So QM map can do things like this given what is really just like a Google type query or something. Don't even need any data. I could then add layers on top of this and print stuff if my latitude and longitude for my points lined up with the points on this. Okay, so QMplot and QMap functions that I just showed are both what I call wrappers for the getMap function. That is, they call a ggplot call with the ggplot plus getMap functions. They put them together into one call. But if you're doing a normal ggplot like call using some data frame, some AES in it, you can add a layer with a map using the getMap function. What that does is it will retrieve some base map layer you want to put as a layer underneath your points, your lines, whatever it is you're plotting that's geospatial. Options that the getMap geometry or getMap function will take are location, which can be either a search query like I kind of showed in that previous slide, or it could be a vector of longitudes and latitudes. So you could give it a bounding box, you could give it a specific point to search at. The zoom is whatever height you want to be looking at above those points. So 3 is basically continent level. If you do 1, it's the entire planet. Right? 3 is a continent, 10 is a city, 21 is a building. So Google Maps actually maps the inside of a lot of buildings, some on campus and like things like malls and stuff like that. Google Map has building level. If you want to plot within it, you can actually just query those maps and grab building level data from Google Map. You can specify the source. So at the time of writing these slides, I'm not sure if this has changed now, but it took 3 different sources. You can get Google Maps, you can get OpenStreetMap, which is sort of an open source mapping thing so people can contribute features and things. So it's kind of a live updated map that doesn't rely on Google to update features. And Stamen maps for more artistic maps. The map types for Google Maps, you can do terrain background, satellite maps, road maps, and hybrid maps, which plots like roads over the top of satellite. Stamen maps can take things like watercolor, toner, I'll show you toner and toner background here in a minute, and toner light, which kind of look almost civil engineering in style. We'll see one in a minute. And then you can specify whether you want a color map or a black and white map. There's additional options that can go in all of these locations too that you can see in sort of a help for it. I'm just going to give kind of a general overview and show some examples here. Here's a toner example. So I've done here QMap. I've centered my map on Pike Place Market, zoom level 14, and I've specified toner background from Stamen maps. So this is a toner map. It looks more like a sort of a civil engineering map or something you might see like provided by the city. So it shows the streets, everything here. It shows plots. Some things are cross-hatched for large buildings and things like that. Yeah, the toner map. Looks nice when plotted with some types of data. Kind of gives you something prettier. A lot of these maps in Stamen and sort of specific use of are great if you want to do maps that you're going to want to sort of like dazzle people with a little bit, like if you're doing posters and stuff like that. You give a little bit of a more stylish map than you might get from something else. They look nice, they draw people in. One of the things about maps that's really nice is if you put a map in an article or something like that, people love it. Basically, if you can find any reason to shoehorn in a map into like a little paper or memo or something like that, people fucking love maps. Yeah, people, I mean, because it's something people can connect to. Everybody sort of is familiar with maps, they know how to read it, and then it anchors them in place. It's great, especially if you're working with like areas people are familiar with. Let's say you're doing a job talk, you go to another university. Let's say you go to, you're given a job talk at NYU or something like that. Plot your data within the New York level like that and show whatever you're doing mapped to that. Like, people love that stuff. We had somebody give a job talk here like last year, and they showed their, they did some map at like Seattle level. I remember, I don't think it wasn't in our department, there was a job, maybe it wasn't, I don't know. Yeah, but it did like their maps in Seattle. People love it. It's like, ooh, wow, look at that stuff. I live there, that type thing. Draws people in, it's pretty great. And then if you art it up a little bit like this, it can be really nice. People like to look at this stuff.
If you're interested in something spatial, and you don't have the data, but like it's all mapped already, like by someone else, is it possible to sort of get it from Google Maps? Is that right?
In what way?
So I'm thinking of like bike share stations, for example, like. if
So
you-
there are points in the Google map?
Yeah, and like, or like I have a map. I actually have it in front of me. It has like bike share stations, public transport stops, and like bike paths.
Mm-hmm.
And say, I mean, I could probably like call someone and try to get this, but if I couldn't, how would I? Is there a way to get this?
There's a couple ways that data may be stored. There may be an underlying Google Doc that is feeding that data to it. If that's the case, you should be able to get the Google Doc, in which case those points will be associated with latitude and longitude.
Yeah.
If instead that is a Google map that is connecting to some sort of like SQL database that is being hosted by somebody else, you might have to get it directly from them. It's very likely that there is some arcane way to directly scrape the data. If it's being displayed on your computer,
Yeah.
you could probably extract it. The question is how to do that. That might be doable. It might be something. I'm sure somebody has some sort of little Python script that scrapes Google Maps pinpoints straight out of a Google map. I would say it's almost certain that you could do that.
And what if it's a route?
A route?
Like a path?
Yeah, so a route should just be a chain of points connected by a vector. So probably be able to extract that. So it should just be, yeah. All that kind of stuff is, it's all vector graphics stuff, so it's just points and then basically like, are these 2 points connected? If so, draw a line. Should be some way to extract that. Who knows how complicated? I never know. Could be a pain in the ass. Often the easiest thing is just to email them and be like, can I just get your data? Because it's obviously public if they're showing it on there. Who knows what format it's going to come in on. So anyway. So here's an example using Google Maps, so a terrain map. Here I just said location Seattle, but I zoomed all the way out to zoom 8, so it's just kind of giving me the entire Puget Sound area within Washington. Map type terrain, source Google. So this looks exactly like what you'd see if you just did maps.google.com and browsed around. To the degree that it even says, as a little Google watermark down here and map data 2017 Google. It basically just screenshots what the website would grab. So it's an API call. It does the exact same thing your browser does when it talks to Google. It sends a search query exactly the same way. Sends it to what would normally return these data to your browser, but instead it sends it to R, grabs it, and prints the map. Pretty cool. It's not doing anything fancy. It's doing exactly what your browser does. We're going to talk about APIs next week a little bit to make it clear what's going on here. Yeah, so you get this. You can then plot data on top of it. So you do stuff with environmental data, things like that, weather data, you can plot it right on top of that. And actually, when you go to weather sites that use maps as a background, they often are just querying Google Maps, grabbing a map, and then printing their own data on top of a Google map. There's no reason to do your own mapping if you can grab it from people who are experts at mapping. So you just have one computer talks to another computer, they work together and spit out a pretty map. Yeah. So, what I'm going to do here is we want to take these incident data we had for Seattle and subset them to only incidents that occurred near downtown so we can plot them on that map I made around Pike Place Market. So to do that, we need to basically tell R what data we want using latitude and longitude to subset. So that sounds like it'd be something challenging, but given that latitude and longitude are just their numeric x and y coordinates, we basically just want to shear off things outside of a box that's governed by some values of x and y. So if we have some map that is like some square here, you know, we've got the waterfront, whatever, we have Pike Place here, what we want to do is subset our data to the individual police incidences that occur within these x coordinates and these y coordinates. Just numeric data. So we can say we want things to be less than this x, greater than this x, less than this y, greater than this y, and subset by x and y. So what I do here is the first thing I do is I get my map for downtown, which is just Pike Place Market, zoom 14, the same map I did just a minute ago. Then I'm going to grab what's called the bounding box coordinates of the data frame. So stored in the attributes of downtown map is this BB object. This is the bounding box. This is the bounding box. The bounding box are the outer boundaries of the map. Normally a bounding box is stored using the coordinate. I think it should be the lower left and the upper right coordinate. So all the information necessary to reconstruct this square can be done from 2 points that are at opposite points. So you just get the lower left coordinate, the upper right coordinate, and because of that we already know what these other 2 ones are because it's a square. So we grab attributes, downtown map, bounding box, so it's an attribute with that name on the downtown map. I haven't talked too much in this class about attributes. If you want to get deep into attributes, you can look in the advanced R textbook that I have linked on the website, get real deep into attributes and all that kind of stuff. Basically, it's another way of storing information about objects beyond actually having rows and columns in the data. Labels for things tend to be attributes, that kind of stuff. The class of an object is an attribute. Anyway, now what I'm going to do is I'm going to create downtown Seattle incidents, the subset. To do that, I have my SPD raw data. I'm filtered down so that downtown BB lower left latitude, that is the lower left corner of the bounding box, less than or equal to latitude in the data frame, and then the upper right is greater than or equal to latitude. So this is exactly what I said here. I've said I want the latitude to be between lower left and upper right, and then I do the same thing for the longitude between lower left and upper right. Right? Makes sense. You could probably write yourself a tiny little function that would automate that if you're going to be working with a lot of maps, because you're always going to be saying, I want this coordinate to be less than or equal to latitude, and I want this coordinate to be greater than or equal to latitude. And since you'll always be using this exact code right here, if you ever want to do map stuff, feel free to copy and use this. Just use it. It's going to be the same for you anyway if you wrote it yourself.
So BB, what BB is like, you name the BB or it's a unique name?
For this?
For, yeah, attribute.
That is, so the getMap function, when it produces the map, it writes that attribute for the bounding box to this location. So the getMap function creates that in the map.
BB, okay.
Yeah, so it's there, and anytime you use getMap, it's always going to be in that exact location. Okay. So you could literally take this entire thing and automate it to a single function and just grab them out there. I didn't because I wanted to break the whole code down, but when I do it, I'd write a function for it. I was going to do it more than once. Okay, now what we're going to do is we're going to do this quick map plot, the same plot as before, kind of, but we're going to throw on top of it a density plot so that we can show the density of these crime incidents that occurred in the city. So I'm going to call QMMap. My data is going to be downtown Seattle incidents. My geometry is blank. I have nothing. So QMMap has slightly different syntax than a general ggplot call because it already builds some geometries in. This is me saying I don't want any geometry by default. X is longitude, Y is latitude. The map type is that toner light map we used before, or we use toner background, it's the same thing. Darken 0.5 is going to make it slightly darker. I forget if it makes it slightly darker or slightly lighter. I think it makes it slightly darker. Then I'm going to say stat density 2D. This is a 2D density plot. We'll see it on the next slide to show what it means. But basically, it's going to draw something that looks kind of like a heat map over the top of it. In whatever color scale I give it, it will be a darker color where there's more events and a lighter color where there are fewer. I'm going to do AES fill equals ... level ... This is how I'm calling on the number of incidents occurring in the location. So this is basically the count. Geometry equals polygon because I'm going to be drawing what is really darkened polygons over the top of this map surface. Alpha is 0.2, so it's mostly transparent. Color equals NA. I don't want there to be a single color. Instead, I want some gradient that goes from low to high. So I'm calling color equals NA. Then I'm saying scale fill. So this fill is going to follow some gradient of colors going from some low value to high value. I'm going to label the legend for it, incident concentration. My low value is white, so the lowest concentration is going to be white. My mid is going to be yellow, and my high is red. So as the number of incidents increases in a given location, it goes from being white to yellow and finally to being red. Okay? Some complexity to that. You can tweak with it if you want to see how how it works, but this is a general way to do a density plot. What does it look like? It looks like this. So, I've taken all these police incidents and then done a density plot. So what it's actually done here is that at given sort of cutoffs of a number of events within a given area, it's drawn sort of like concentric ovals, things like that. So it's basically saying if you have events like if you have things spread out like this, what the algorithm for the density is doing is it's more or less coming to being like, okay, at this spot, how many events occur within here? 0. Let's assign it white. How many events happen within this spot? Oh, 4 events. For this data, that's a lot of events. Let's assign this red. Next spot. But imagine it did that over every overlapping spot on the map, like one after another. You'd end up with different locations that have different colors assigned to them, and it will smoothly interpolate the colors between those points. That is, do a smooth fade from what is this white point to this red point to this yellow point. So normally there's different algorithms for calculating this. It's commonly things, if you've heard the term kernel density is a common way of calculating this. The spatial stats class will talk about density measures a little bit. That Bivan book will talk a lot about density. Anyway, this is a density map. One thing you'll note here is that as you get closer to the edges of the data, there's always very low to 0 concentration. And that's because if you're doing circles to assign density to things, down here at these points, there's no events down here, so you can't have much of a density for events occurring because we've chopped off all potential events here. Your density plots are always going to kind of taper down to having no events here. A trick, if you don't want that to happen, is to actually subset your data wider than you want, and then at the end, clip it down. If that makes sense, sort of crop it down. But anybody who's familiar in any way with mapping this kind of stuff knows you're always not going to have reliable estimates of density on the edge of a space. It's just the way it works. We'll talk about that in the geospatial stats course a lot. Okay, so what do we see for hot points? We see like hot points for crime occurring down here in this sort of like Pioneer Square area, and then down here in this sort of what's up? Yeah, that is kind of like ID Pioneer. I can't quite see the streets. Anyway, there's 2 locations that always have a shit ton of crime in Seattle. Those are them. Yeah, so we have a useful density map. Cool. So, if we have densities and stuff like that, maybe we want to label particular events instead. So we might know lots of events happen here, but maybe we want to see where rare events occur and then label those rare events. Good examples might be things like armed robbery, which doesn't happen that often in Seattle. We might want to see those exact ones and then label them when they actually occur. So what we're going to do here is I'm going to label the assaults and robberies that are specific to this downtown area we're currently working with. I'm going to create a new data frame called assaults, which is equal to downtown Seattle incidents, mutated a new variable called assault label. So this is going to give a label specifically when the event clearance group is in assaults or robbery. How do I state that? So what this is doing is that we want to plot the label for all of the events, but we only want a label there if it's an assault or a robbery. So what I've done is if in the event, so the type of crime that occurred, if it is an assault or a robbery, the label is going to be equal to the event clearance description. That is the description of the crime that occurs. If it is not an assault or robbery, I want nothing there blank. If it's blank, it's not going to draw a label, right? So I've essentially drawn labels only for the things that are assaults and robberies. And then filter if that assault label does not equal blank. So if I did instead, this did here, I could replace that with like drop, and as long as this was drop also, it would also remove it. It's just a way to filter out all the ones that don't have this label. Slight roundabout way of doing it, but it's the way I thought of it. So now we're going to actually plot these things. We're going to plot them using geom label. You could also do this with geom text. Difference between geometry text and geometry label. Geometry label draws like a little background plate behind things, which is good on top of maps, because maps have a lot of stuff going on in the background that can make it harder to read the text. So we put a little plate behind it. Code for that here. Do the same QM plot where we have our downtown Seattle incidents, longitude, latitude, toner light map again, color fire brick, alpha 0.5. So this is drawing all of the incidents in the data, not just the assault ones. But then the label I've added is geom label, a different data frame, which is our assaults data, AES label equals assault label. So what this geom label is going to do here is it's only going to plot points for within this particular data set, which is just the assaults, and the label it's going to draw is equal to this assault label variable we created up here. It's still going to have for the points on the map all of the different crimes. Right? So we're highlighting the ones that are assaults or robberies, but we're keeping all the other data on the map too. What's it look like? Here we go. So this is an example. This is it could be a little hard to see, but these labels actually have a little black line sticking out that points to the specific point they're referencing. It could be a little bit hard to see. Might be easier to see on some of these. That one there, I should have made it a different color, make the surrounding thing like something bright, or lighten the back map, but that's what we got. Now, we see an obvious problem with this particular map that we just drew. A couple things. One, in some of the crap areas of town where a lot of these things happen, so they managed to have 2 robberies and a firearm assault occur in a very small area down here in kind of like the Soto district. Enough that they're overlapping. We don't like having our labels sticking on top of each other, makes them harder to read. We also have one cut off over here on the right. Right? So, what to do about that? There's a package specifically for addressing this problem. There's a package called ggRepel. What ggRepel does is it imposes a little bit of gravity on these labels to push them apart when they're normally overlapping. This is a package that back in the day I did not know existed, and I attempted to code this myself to make labels oppose each other. It turns out writing a gravity model is not very easy, especially when you're a crappy coder like I was a couple of years ago. Total boondoggle, never got it to work right. And of course I found out that other people who are better at coding had done it, and it works really well, so wasted effort. Google what you're doing before you start to sit down and code. Anyway, so what we can do is we can call on repel versions of label and text instead that will automatically repel labels from each other. They are geom label repel, geom text repel. They, aside from the extra like repel functionality, work exactly the same as label and text. So same map we just did before. Now we've used geom label repel. And then I've specified segment color equals black, was specifying the little line that sticks between the point and the label is black. The label itself is filled black, the color is white. So I've changed my label colors, which we'll see here in the next one. It's otherwise the same. Makes it a little bit more readable. So what we have here are repelled labels. They no longer overlap each other. They push apart and they draw that little line to the point. So you can kind of see down here where it's a little busier, there's actually, unfortunately, they're kind of lined up with the streets, but there's some lines drawn like there and there and stuff. So I might change the color on that or make the back map lighter if I was going to do this again, but these were kind of hastily put together. You also note that not only did they repel one another, this label actually got pushed back into the sort of bounding box for it, so they don't just repel other labels, they also repel the edges of the plot. So almost no reason on a map to ever not use repel, because they just kind of make it better. Might want to not use repel if you're using really small, simple labels and you actually want them to overlap, like pins on a Google map. Sometimes if you have lots and lots of pins, you want to overlap. If not, you just have a uniform distribution of little pins covering the entire map. If you have a lot of points, probably don't want to repel them. But if you have a lot of points like that, you should be plotting with points anyway rather than labels, but who knows what you're doing. You do you. Okay, now, we've been using ggmap up until this point. We can do all of the things we just did, be a little harder to add Google Maps, statement maps, and things. But we could do all of the things we did before using just ggplot without the ggmap functions at all. So, and this is really common. So if you're working with geospatial data and you don't want like a Google map background, some kind of raster image or something like that, you're grabbing from another place, most people just plot their geospatial data on a normal ggplot call. I mostly call things directly from ggplot. Let's say you get boundaries like tract or city boundaries from the census, which we're going to get to later today. You'd usually just plot them using ggplot instead of qmap or something like that, because you don't actually need that map in the background. You could link all this together if you wanted, though. So, with given x and y coordinates of any kind in some kind of data set, you can just use those x, y coordinates to draw the points and the lines that define whatever geospatial objects or data you're working with. All you need to do is you need to provide ggplot with the following. You need to give longitude as the x-axis, or as the x-aesthetic, latitude for the y-aesthetic, and then if you want, some data to fill in whatever polygons you're making, say if you're making like a choropleth map. A choropleth map is just a map where you have a bunch of polygons, usually contiguous polygons like these, and then they are shaded some color or some gradient to indicate data occurring within them. This is really common with census type data because it's usually collected at tract level or block group level. You might shade them for some particular reason. I have some examples come up in a bit. So, what I've done here is I've grabbed the Seattle tract data. So this is a little bit of a subset of data from some of my field experiment work from the last 8,000 years that I've been doing field experiments that I'm going to use normal ggplot to sort of plot on a map. So, here's a rather complex, daunting looking code for doing a choropleth map using geom polygon, but about 2/3 of the code here is unnecessary and is me just removing things from the plot because it was ugly and too complicated. So what I've done here is I've done ggplot, the tract data that I have, which just has x, y, longitude, latitude to draw like tract lines around it. My group is group here, which is actually just each group is a particular census tract. My fill is going to be this variable concentrated disadvantage, which is a tract level index of it indexes all of the types of socioeconomic disadvantage that are normally recognized at neighborhood levels. I've just then done geom polygon. That's going to, without any additional arguments, it's going to draw these longitude and latitudes as polygons, where each group corresponds to one particular polygon. So all the xy coordinates will be all the points connected by a line that will draw a polygon. I'm going to do the fill as a scale fill gradient going from low to white, high to dark red. So as concentrated disadvantage increases, the polygon will get darker and darker red. Coordinate equal is just a way of equalizing the coordinates so that my latitude and longitude make a nice, basically, so my plot isn't like squished in some particular way. Then I've done geom path color equals black. We'll draw a black line around those polygons. I've set line type 1, which I think is a solid line. Then this big call here is me just removing things. I don't want an axis title, I don't want axis text, I don't want grids, I don't want a background, I don't want ticks, I don't want lines. So I do element blank on all of these things. Then I add a label, title concentrated disadvantage, fill equal to disadvantage. What's this plot look like?
So data has the shape of polygon, or?
Yeah, in this case I do. So these data are set up such that they're huge. This is actually a really big data frame. But this is the best way to get data into like ggplot for mapping it. So what I have is say, I'm going to say it's like I have tract 1, 1, 1, 1, 1, 1, 1 going on for maybe 300 rows or something like that. And then it has a x and it has a y. And then each of these are the coordinates for a given vertex going around the polygon. So let's say you have a polygon that looks like, like a pentagon. This polygon could be drawn with 5 coordinates, right? You need 1 coordinate for each point on it if these are straight lines going between them. This polygon would have 5 rows of data. It's one way of storing geospatial data. We're going to talk about another one sort of at the end of this. This is more recent. But the sort of simple tidyverse way of doing it is every vertex gets its own row with an XY coordinate. Makes a really big data frame, which is annoying, but it's really easy to process because that's what ggplot is expecting to come in, as every point is that. Then what you do is to tell it that you want a polygon, this entire thing, to say this would be group 1, it would associate all these points with each other. Say you had another thing right here, this would be group 2, so on and so forth. Then it just knows that each group is going to be a polygon. It knows to draw a line around the boundary of this, and it knows to fill it with a particular color. Yeah. So we're using standard ggplot type functions, just in a little bit different way than we've done before. Yeah, so each row corresponds to a point, a vertex of a polygon rather than that. And so every single one of these rows, so if there's like, let's say you've got like a track that has 30 rows to it, every one of those rows is going to have the exact same value for like concentrated disadvantage or whatever like that. It's just going to fill the whole thing with the data for that. Okay, this is what it looks like. So it's slightly rotated here because the geographic projection I'm using is actually centered on a different portion of the Earth, and we're being projected away from it. We'll talk about projections in a little while. Anyway, because of the contours of the Earth, this one's at a slight angle. What I've done here is this is every year 2000 census tract in Seattle, excluding Georgetown, kind of Sodo area right here, because that tract is really weird. It has like 2,000 people living in it, but it's the size of, it's just absolutely massive. It's almost all industrial. Excluded it for this because its measurements make no sense. Anyway, so this is a choropleth map. As it gets darker here, we get higher up this index of disadvantage we're working with. As it gets whiter, it's getting lower, right? So you can see that the areas of high disadvantage in Seattle are pretty particular. It's sort of like pocketed in different places. So we have this sort of central district in South Seattle area here. We have this one particular area here over in West Seattle, which actually contains a very large low-income housing project, which is actually why it's dragged down. You know, and then we have the sort of South Lake Union. I tell you what, these are 2000 data. That does not look like that in 2015, like in the ACS data. But Seattle's changed a lot in a few tracks. Anyway, but year 2000 data looks like this. Here's another one. This was me doing one with collective efficacy. So higher collective efficacy are basically neighborhoods that are better able to sort of regulate what goes on within these neighborhoods. You get these high blue stuff, sort of, especially places like Laurelhurst, Northwest Seattle, parts of West Seattle, less so in Central Seattle, some areas in like the Central District and South Seattle. Basically an inverse relationship between these two. Yeah. So that's the actual data I work with. This is an old map I produced for some of my own work. I would do this with different methods now, but it's a good example of how to do it using sort of very plain ggplot given some kind of data set. And the data set I've used for this, you can actually download straight off the website and see how it's formatted to give you an idea how it works. Yeah. It's another one, log of crime, so log count of crime, basically crime rate stuff. Also, there's a inverse relationship between collective efficacy and crime, so we would expect theoretically. Yeah, so sometimes you just do like multiple essentially facets of a map. It's nice to show lots of different indicators like that, give it to people in a memo. My professors love it when I throw the maps in a memo. They're like, oh, this is great. They look at the stuff and like, now you're pleased with me. That was surprisingly easy to code. It's the little things. Okay, now we're going to talk about tidy census. So, tidy census is something new to me. I only learned about it maybe 2.5 weeks ago, 3 weeks ago, because I was thinking to myself, I was like, there's got to be an easier way now to do census data than the classic way of doing census data, which is, well, I know there's better things than American Fact Finder. So American Fact Finder is the web interface for the census. You go on the census website, you tell it what you want. It's bulky, it sucks. It's just a giant piece of shit. Anyway, you browse through it, you have to like select all the variables you want, but the variables have arcane names, they're hard to look up, it's a huge pain, then you gotta download them as like Excel sheets. So there is a package, as a normal census package, that allows you to sort of extract and grab the data given some census API directly into R, but it doesn't necessarily give you geographic information, and it tends to come out in ugly list formatted data. So I'm like, is there something that puts out nice data frames of census data so that I don't have to reformat them? Turns out there is. There's Tidy Census. So, what Tidy Census is the package that you can first use to search within the American Community Survey, which is done basically constantly. It's a rolling survey every year. They interview more people, and it's used to sort of update census stuff. So smaller samples, great coverage though, done every year. The ACS is actually generally considered more accurate than the decennial census for a lot of different things because it's randomly sampled, whereas the decennial census is inherently biased because it attempts to get a full population. Anyway, tidy census will allow you to search within the ACS and decennial census for variables, download them, and then automatically format them as tidy data frames with all of their additional information attached to them, so you know what you're getting. These data frames and downloads you can tell it to give you the geographical boundaries associated with them. If you ask it for census tract level data, it will also return census tract boundaries that can be plotted. So everything in one place. You don't have to go link your geospatial data up to your census data and merge them together. It all comes in one data frame. And it utilizes the Census API, which means you're talking right to the Census Bureau. It's really convenient for getting the data, but it does mean you have to get a Census API key. If you Google get Census API key, it'll probably take you straight to the webpage. It takes like a minute to get a Census API key. They don't do any checks on your credentials. The only reason that the Census Kit gives you an API is to make sure you don't overload them with requests. Once there's an API key, that attaches it to you and your computer. So if you start doing 1 million requests a minute to them, they can shut your API key down briefly. It's just a rate limit. Every online service that has an API, that is an application programming interface, uses APIs because they let you regulate how many requests you make, so they don't have to just block your entire IP address when you start asking them for too much stuff. Yeah, and if you do ask almost any website for too much stuff, like you're scraping data, pretty much every web server nowadays has automated ways of shutting down IP addresses that are basically doing a denial of service attack. So don't do that. Okay, so load up tidy census, and normally you only have to do this, I'm trying to think if you have to do it only the very first time you load it or in every main script. But basically there's a function in tidy census called census API key. As a character string, you'll put your API key that the census will give you there. Install equals true will save it into your, I think it saves into your .r profile or your R directory. And then it'll just work from here on out. It knows where to find it. Okay. However, if you want to plot using tidy census, at least last I checked, the plotting functions that are compatible with the type of geospatial data in tidy census are not part of ggplot yet. They're in the development version of ggplot. So, and this will change as soon as the geometries for SF objects are finalized. I'm going to talk a little bit more about what SF objects are. It's an entirely new way of handling geospatial data in R that mirrors the way geospatial data is actually handled in GIS software. So this is really good, but it's incompatible with past stuff. ggplot has new routines, new functions for handling SF data, but it's not, as far as I know, in the release version of ggplot yet. So, if you want to use tidy census, at least right now, you have to install a package called DevTools, which are the development tools for R, and in that there's a function called install_GitHub, which lets you call directly to a GitHub repository. This is the username for the GitHub, and then their subfolder and their that user, so the repository for this particular user, and it will automatically grab our packages and install them from those locations. So what I'm doing here is I'm just saying, go to the tidyverse user on GitHub, download the development version of ggplot2. Has some new functions added to it. So, once you've done that, you'd be able to plot. In tidy census, there's really only about 4 key functions in tidy census that you would want to know how to use. The first one is that census API key for installing your census API key. There's a function called load variables. What load variables does is given arguments like ACS, ACS5, ACS 1, different levels of the American Community Survey, or given decennial census, what variables do I want to search for? And there's a lot of different ways to search for them. You can search by the concept, things like race, income, things like that, or specific variables, or give you everything. You might just be like, let me see every census variable.
Does this only work with American censuses?
Well, yeah, this one is, because this links directly to the US Census API,
Yeah.
it's very specific here.
This tidy census.
Yeah, tidy census is specific to it. Other countries, if there might be packages for them. There's one for the Canadian census, but I haven't looked for anybody else's. Might be something, never know. It hinges on there being either an outside developer who wants to produce a package to do it, or the organization itself producing it. The U.S. Census produces really great R packages. They have some great stuff out there. Just they didn't have their package by default doesn't produce tidy output or grab simple features geometry like this one does. I don't know. So if you want to Mexico, no idea. You have to look. But you could probably get data from them one way or another. Worst case scenario, scraping directly from the website and format it nicely. So, load variables will grab basically the entire list of all the census variables, which once it's on your computer, you could then do string searches from like last week, things like that, hunt around in them, try and find the variables that you want. Next, there's the two functions getDecennial and getACS, which will load census variables and their geographical boundaries based on variables that you might select from within load variables. Basically, this gets you the variable names, and then gets decennial. You could provide it a vector or a list of variables you want to grab. It will grab them, automatically put them in a tidy data frame with their geographical information, and it will do it at whatever geographical level you ask for. You could ask for tracts, block groups, you could ask for cities, counties, states, whatever. You just tell it state, city, county, whatever, it'll spit out. Actually, I won't do city because city is not a census recognized size. County, it's county and then census tract. Anyway, it'll do it. So, this is what searching for a variable looks like in it. What I did here is I said, I want to load variables from the 2015 American Community Survey 5-year estimates. So these are basically the estimates generated by 5 continuous years of the ACS. So I think it's more or less the mean across those 5 years, so it's adjusted. For 2015, and then what I did here is, this is just code where the first variables were uninteresting, so I just grabbed the 10th through 18th variable and printed them. This is the kind of stuff that you get. These are the actual census variable names. So if you wanted to go through the like American Fact Finder, these are the variable names that would be listed, but they have a label associated with them. Things like, this is the population of males under 5 years old, males 5 to 9 years old, males 10 to 14-year-olds, population count of all males, the total population, so on and so forth. There's another column called concept, which captures the general type of variables that all of these fall under. Concepts tend to be really broad and have hundreds, if not thousands, of variables within each one, so you don't want to search purely by concept. But yeah, you could look at a huge list of this, and then these are just strings. So if you know more or less what you want, you just do a string search within the label here, and then find the ones you want. And in the census, there's a lot of duplicates, like total population is duplicated like a couple hundred times in it, so you usually just grab, like, I normally grab 2 or 3 of them, make sure they're all equal so I know I'm grabbing the right thing, and then take the first one. Yeah. So you can just search within that. Okay. So what I did here is I figured, okay, this is actually for some of my work for Ross. I wanted to get recent accurate estimates of the concentration of individuals reporting to the ACS that they are either black or multiracial, including any black. Because we were interested in, I think this is tract level diversity for our field experiments, in which we were looking at how people react to people of different races littering in front of them. Spent all summer littering in front of me. Fun times. Anyway, so what I did is first I searched down in these variables for what is the total population and what is the population any black, which is the term the census uses for people who responded any black on the race variables. So total population was B02001_001E, which I think is actually, yeah, it's basically the same as this total one, but it's in the next series of variables. And then this one was any black, and these are counts, right? So get ACS, geography, I wanted tract level data in the state of Washington and King County. Geometry equals true says, please fetch me those tract boundaries. These are the variables that I want, so it's a vector of variables. Then this getACS spits out something that's already in a tidy format, so I can drop it right into a dplyr call. Okay? Now what I do here is I said select minus MOE. So the reason I'm dropping this, MOE is the margin of error. I can't easily and cleanly spread my variables without dropping this MOE. Nothing special. Basically, there's a margin of error for every single one, so it means that for this variable, I have both a value and a margin of error. I only care about its value, so I drop the margin of error. Then I grouped by GOID. GOID, like this, 53033000100. This is tract number 1 in King County. Actually, in Washington, King County, tract 1. And you can see it has a name to replicate that. Census Tract 1, King County, Washington. Other variables it grabs are the geometry, which is stored in a unique way I'm going to talk about in a minute. Then total population and any black. Then what I've done here is I've calculated any black to now be a ratio of black to total population to get the proportion any black in the tract rather than the count. Okay. And also you see here, because it spits out the variables in the census variable name, you're going to want to rename them if you actually want to use them. Okay. This code you can more or less copy exactly like this. If you want to use tidy census, replace your own variables in here. This will clean it up to be exactly the way you want it for mapping. Have any questions about that? It's a little complicated.
What does the spread command do again?
Good. Yeah, I should have mentioned that. So what I'm doing here is the original format it comes in is a tidy format, but the tidy format looks like this. Okay. So you have a data frame that comes in with the GOID, so that's like the tract level or state level, whatever indicator you're working with. It then has that name there, but then it has the variable. Instead of giving each column as a variable, it gives one column called variable, and then within it, the value would be, for instance, this would be any black, or total pop, so on. So if you have every location, it's going to have one row for each variable, and then the value for each of those variables over here, right? So if I want it so that each of the variables I'm interested in is actually a column instead, I want to take this key and this value, spread them out, and convert each one into a column. So in this case, I've used spread for that. The reason it spits out like this is it's very common when you're using census stuff, and you might want to grab a couple hundred variables, and rather than defaulting to giving you a couple hundred columns, it defaults to making it a long data set, which is easier to look at, and you can always spread over it. So sort of in tidy formats, we like to keep the data sets relatively narrow. So by default, it does that. And the reason I couldn't spread without dropping margin of error is that you'd have for each one of these variables, any black total population, there would also be any black margin of error, total population margin of error. I didn't want to spread those ones out because I wasn't interested in them, so I just dropped it's not each one here. Instead, there was an MOE here and then a value here. So spread only lets you spread over one key and value, not one key and two values, at least not that I'm aware of. I could be completely wrong. So it didn't spread nicely, so I dropped MOE.
So value means like estimate?
Yeah. The estimate, so the variable is whatever variable you're interested in, and then the estimate is whatever number it would be.
Okay.
So it'd be any black, then the number of people who identified as any black, or at least the estimate of number of people. Since the ACS is a random sample, they're estimates with a margin of error. Even the decennial census will be an estimate with a margin of error, even though it's a biased population sample. Yeah. Okay. Now, I want to actually map this shit. So, what I did is I have this King County data frame, which I created right back here. ggplot, AES, the fill is any black. Notice the only thing I did here is I gave it a fill. I didn't give any XY, I didn't do anything. All of the actual mapping is going to be taken care of by geom_SF. So, unlike the previous examples I used with ggmap and things like that, tidy census spits out data in this more modern, simple features format where ggplot just already knows exactly what to do with it. You don't have to tell it anything. It recognizes it as geospatial data. All you have to do is say, plus GeoMSF, it will look for the geospatial data stored as what's called simple features geometry and plot it. The only thing I did here is I modified it slightly. I added this additional argument here, coord SF, where I modified its projection. So basically, because the Earth is spherical and we're looking at things two-dimensionally, you have to have some way to translate our latitudes and longitudes, which are based on something spherical, to something flat that looks sensible and is minimally distorted. There's a million different geographical projections you can use. By default, it came out with a projection that skewed my, basically it was a little scrunched. I think it was scrunched a little horizontally. So what I decided is like, okay, I want to use a flat projection that's very commonly used called WGS84. WGS84 is actually the conical projection method used by GPS satellites, so it's about the most commonly used projection. When in doubt, use this coordinate representation system. I just said plus proj equals lumlad plus datum WGS84. Use that. Pretty much every map you ever do will look nice in WGS84. If you plot something with GeoMSF and it looks ugly, very first thing to do, go to WGS84, see if it looks nice. It'll probably look like shit if it's at the North Pole or the South Pole, but it'll look good for the rest of the world. Then I did this datum equals NA. Datum equals NA removes graticule lines. So the graticule lines are the actual vertical and horizontal lines for latitude and longitude on maps. In this particular map, they just looked ugly, so I said NA, get rid of them. You can leave them on and you'll still have them there. I just thought it was a little messy. Otherwise, normal ggplot call stuff. Scale fill continuous is going to let me control the color range for this any black variable. And I just said the name for the legend on the right is going to be any black. The /n there is because by default ggplot sometimes draws the legend label too close to the actual color scale. /n is the escape character for line break, so just bumped it up. Basically like hitting return at the end of a something in like a text editor to bump it up. Low color was some hex code I grabbed for, forgetting what color scale I'm on. Something low, something high, just arbitrarily grabbed some stuff off the color wheel, make it look nice. Theme minimal gets rid of just about all of the random crap like axis labels and stuff like that. Then I added a title to it. Looks like that. That's the entirety of King County mapped by proportion any black. Didn't have to do any real data processing. Got the entire like geometry, all of the individual census tract locations in King County, and the plot's nice. Yeah. You can see there's some gigantic census tracts in King County in the places where there are no people. Like you could fit all of Seattle inside that. Yeah. You have any questions about what's going on here, other than what is GeoMSF? Basically just copy the code on these two slides for any census stuff you ever do. It'll work. Cool. So, if you want to get deeper with geospatial data in R, up until recently, as I say up here, the main way to work with geospatial data in R, including the way described in that Bivan book at the beginning, was with a package in R called SP. SP is the spatial package. SP works really well. It has a lot of functionality. It has a million different things it can do. It handles geospatial statistical stuff incredibly well. But the thing is it doesn't store geospatial data in it the same way that GIS packages store their data in it. As a result, it stores data a little bit bulky, big, lots and lots of rows and things like that. And it's complicated, and because the SP package is an old package that's sort of been just developed on top of for a decade or more, actually 15 years or something like that, it's kind of complicated. It doesn't always behave in an intuitive way across all of its functions. So the people who wrote the SP package originally have started developing, and are basically, I think mostly done developing, the SF package. The SF package implements what's called simple features spatial data encoding. This is a link here, I think probably to Wikipedia if you're interested in what that is. Simple features is the modern International Standards Organization standard for storing geospatial data regardless of where you're storing it. So every geospatial database basically stores simple features data this way, or stores geographical data as simple features data. Every major GIS package stores all of its geospatial data as simple features, things like that. It's basically universal. So they had the idea, it's like, well, if every other damn thing is storing their data in the same way, we should probably have R stored the same way too. So they did. The neat thing with SF, though, is this is a modern package. They've made it so it's cleanly integrated into all of the tidyverse packages and things like that, because Hadley Wickham, among other people, Hadley Wickham being the sort of chief data scientist in the tidyverse, is one of the people who's an author of the SF package. So he's on board making sure it integrates nicely. As a result, ggplot is gaining this geom SF, which will automatically read geospatial simple features data and plot it nicely without you having to tell it to do anything. The package is kind of new, but it's actually going to completely replace the SP package eventually. So if you're starting to learn geospatial stuff in R, learn the SF package. It's a little new. You'll have to sometimes learn how to convert stuff from SF back to stuff compatible with SP, but the future is in SF and in simple features. And the nice thing, you learn how to navigate simple features in R. You'll also know how to navigate geospatial data in any GIS software or geospatial database that exists, because they all use the same thing now. Yeah. So basically, if you're going to do any GIS, period, whether you're in R or anything else, you're going to have to learn simple features anyway. And the way simple features sort of stores its data is, instead of doing X and Y coordinates, each as their own column, it stores it as big binary strings of data or big character strings of data. So there will be basically a column in the data frame that is incredibly long that encodes all of the relevant geospatial information across it in a way that is both machine and human readable. So if you get it in, it's like they call it it's like human readable text or something like that. If it's encoded in human readable text, you could actually read the simple features geometry and read it out and then draw a map along with it. It's pretty neat. Anyway. Learn SF. And the SF package will make our lives a lot easier for doing this geospatial stuff in the future. I had to learn the SP package. It actually is kind of a nightmare to navigate. Yeah, pretty cool. So, last thing. There is a homework 7, but it is a practice type homework. If you're interested in geospatial stuff, it works with that restaurant inspection data. So originally I had some lecture stuff using the restaurant inspection data. I swapped it all to the police data and the census stuff. So the restaurant inspection data. So if you want to see the exact locations of the filthiest restaurants in Seattle and things like that, check your homework out. I will say that I live behind a restaurant, and it turns out it's one of Seattle's cleanest restaurants. It's like never had a health violation. Made me feel real good about eating there all the time. Yeah, if you submit it on Canvas by midnight Tuesday the 28th, I will grade them, and they'll just be bonus points. So feel free to mess with it, go for it. If you show up on lab on Monday, we can work through any kind of stuff, and like usual, I'll answer any kind of questions. So that's it for mapping. Cool, thanks for showing up.
So, do you think that ArcGIS still have advantage compared with the R?
With R? Well, it's different. So Arc is an incredibly powerful platform for doing geospatial stuff.
I have an image like Arc has like kind of regression model.
Yeah, it can do that. For geostatistical stuff, it doesn't really hold any advantage over R. If you want to do geostatistical stuff, the most advanced geostatistical stuff is all in R and not in Arc.
Okay.
But normally what you'd be doing is you're using Arc to do like advanced layering of geospatial data, lots of stuff looking at the maps and mapping in a nice way, which is easier to do in Arc nicely than it is in R because of the graphical user interface, all that kind of stuff. Normally what you would do is you would feed data between Arc and R back and forth, or between R and QGIS. So QGIS is the open source one. I was trying to use open source software. QGIS is actually, in most cases, faster than ArcGIS, except in some cases, to my understanding. Arc is really fast at some stuff people commonly do, though, and it's a really refined product. For actual geospatial statistics, geostatistics, I'd be doing pretty much all that stuff in R, unless it's the stuff Arc is really good at. Arc is probably going to be good at stuff commonly used in transportation. Actually, there's transportation-specific software if you want to do transit-type stuff. Arc probably does stuff really well for environmental-type stuff, like creeking for resources and stuff like that. But most things, the cutting edge stuff is
Easy enough.
in R or Python. Yeah. Yeah. So by and large, I would use. I mean, I do all my GIS stuff in R, but I'm also not a hardcore GIS guy. The hardcore GIS guy who I know and work with, he works in both QGIS and ARC, depending on what he's doing, and then feeds stuff back to R.
Okay. Yeah, I have very specific